John is joining us. John Curry is joining us in virtual space. We
Right.
believe he's in his living room.
That's
It
where I
looks like
am.
it's his. You could have put a background in or
Yeah,
something.
I suppose I should have. Huh?
I mean, it's like we've got these fancy telescopes behind us. You could have at least put a star field. So you got a
Yeah,
couch.
yeah.
Yeah. All right.
Yeah,
Well, that's fine.
or maybe the bridge of the USS Enterprise, the Starship
Yeah,
Enterprise,
something like that.
something.
Yeah.
You know,
Yeah,
Right.
well, not very
come on,
exciting.
John.
All right. I'll see what I can do here.
Uh-oh, the telescope's moving.
Well, you sit on the sat on the joystick there for a second. Yeah. Well, those of you who live in Oakland probably looked out the window tonight and realized that we're at 100% humidity. So since we can't even open the dome when it crosses 85%, and 100 means we're completely socked in with fog, our program tonight is going to be fun, but mostly showing pictures that other people have done or pictures from past observing sessions with Nellie. We do have some good interesting things to show you tonight. It just won't be live telescope viewing as in
It'll be
previous weeks.
virtually virtual.
It's virtually virtual. We had a pretty good run. If you think about it,
Yeah,
if
really.
you think about it, I mean,
Yes.
even with through the smoke
Hey,
and all of the other disasters befalling us, we've had a really good run of clear nights, and I'm not terribly surprised that we got skunked tonight. So,
hey, look, John's now in Dr. Morbius's lab.
Yes.
much better.
I'm in my
Much better
Krell
there.
my
There we
Krell
go.
lab here.
Well, or then again, maybe that's where he really is, and he put up a picture of his couch.
Right.
When he first joined.
Virtual couch.
Yeah. All right, Gerald, you have an announcement. We get to model.
Well, why don't you stand up,
All
Rich?
right. Yeah, I get to model.
Richard is wearing a really cool T-shirt, which some of you may recognize if you've been around for a while, especially if you've been around the Bay Area. This is a shirt that was pretty popular here 3 or 4 or 5 years ago, and it's back. In the spirit of community and curiosity and the inspirational beauty of the cosmos, Chabot has once again collaborated with the Oakland business, our beloved Oakland business, Oaklandish, to relaunch this stellar new T-shirt design. A lot of people have been requesting this T-shirt. This was out, like I say, several years ago. A lot of people have been requesting it, including Bobak Ferdowsi. And some of you may know Bobak Ferdowsi is Mohawk guy, NASA's Mohawk guy on the Mars Curiosity rover team. And he was a big fan of this shirt, and he's been asking if we could bring it back. So Oaklandish and Chabot got together and said, yes, we can. So the shirts are now once again available. You can pick them up on the Oaklandish website, which is a really easy website to remember, oaklandish.com. And Oaklandish is OAKLANDISH.com, oaklandish.com. One of the cool things about this shirt is that it glows in the dark. So you stand in a lighted room for a little while and let it absorb some photons, and then you go outside and the shirt will glow in the dark. These shirts are available in adult sizes only, but they range from small to 3X in size. So if you want to buy some for your kids, you have to get the small size, but they will grow into it. And one of the things we want to be sure to point out is that proceeds from the sale of this shirt or a portion of the proceeds anyway, go to help Chabot Space and Science Center. We get 10% of the proceeds. So we certainly are looking for lots of ways to help us financially while we're closed for the pandemic. And so if you want to get yourself a really cool T-shirt, check out the Oaklandish website. They've got a couple of other cool things on there too, including some really interesting leather, what do you call them? Coasters for your cups. They're leather coasters, and they're made by a couple of little girls in Oakland. So you want to check those out. And there's actually a Chabot coaster that you can get. So check out oaklandish.com and get yourself a really cool Oakland Universe T-shirt. All right.
You did very well with that.
All right.
You
Yeah.
got a future in advertising. We don't Later
Please,
on, we'll
please.
have you read the mattress ad and the Arby's. No, all right, enough of that.
We have the meat. Speaking of which, let's see some pictures. So,
right,
so
where do we
once
want to start?
again, we have lousy weather tonight. If we had good weather tonight, we would be showing you pictures or live views of Jupiter and Saturn and Mars. So instead of showing live views, we're going to show you a couple of images here, some of which were taken with Chabot's telescopes and some of which were taken by other telescopes. So let's start with Jupiter. Richard, have you allowed me to share?
Yeah, you should be able
Okay,
to share.
okay. Hey, hang on here just a second. And there you go. So this is an image of Jupiter actually taken with the telescope behind Richard and I. I think this was taken in 2015 by Conrad Jung. Conrad Jung is the staff astronomer up here at Chabot. And he combined several images taken with the telescope to produce a pretty darn good image of Jupiter. And if you look down at the lower band there, you can actually see the great red spot. So Jupiter is the largest planet in our solar system. It's a gas giant planet. It's 11.2 times the diameter of the Earth. So it's much bigger than the Earth. The Earth is just under 8,000 miles in diameter, and Jupiter is about 88,000 miles in diameter. It's a gas giant, so it's a big ball of very dense gas with maybe a small solid core way down deep in the center. So basically, it's a whole bunch of clouds. Now, Jupiter's day is very short. It's only 9 hours and 50 minutes long. So you think about that, you've got a planet that's 11 times bigger than the Earth, but its day is less than half as long. So as you can imagine, the rotational velocity at the equator is pretty darn fast. And because of that, high and low pressure areas in the atmosphere actually get wrapped around the planet. So if you were to, watch your 11 o'clock news and see the weather broadcasts, and they'll show you highs and lows, and they mostly are little spirals or swirls in our atmosphere here on Earth. On Jupiter, it's a little different. Those highs and lows get literally wrapped all the way around the planet and produce those bands that you see. So the dark bands we call belts, and the light bands we call zones. And they roughly correspond to high and low pressure areas. So the dark ones being low pressure and the light ones being high pressure. The atmosphere is primarily hydrogen, but there are other gases as well in the atmosphere, notably methane and some other organic compounds and so on. And the highs and lows, especially the low pressures, tend to churn up the stuff that's deeper in the atmosphere, and so they appear darker in color. Because Jupiter rotates so rapidly, when the red spot is visible, it's only visible for about a 4-hour period. So at any given time when we're looking through the telescope, we may or may not be able to see it. And if we do see it, we have to look quick because it doesn't last very long. Now, Jupiter also has 4 big moons called the Galilean moons. They were discovered by Galileo in 1610. And those moons are Io, Ganymede, Callisto, and Europa. And they are pretty big moons. 3 of them are actually bigger than our moon. And they're so big and they're so bright that you can actually see them from the Earth, even with a pair of binoculars. And they're very easy to see even with a small telescope. They orbit around Jupiter fairly rapidly. In fact, Io takes less than 2 days to orbit around Jupiter. So if we're looking at Jupiter over a period of, say, an hour or so, we definitely notice the motion of Io over that 1 hour period.
Hey, Gerald, while you're on Jupiter,
Yep.
We have a question from Facebook from Laura. Wants to know, why are balls of gas considered a planet? a question I've had since I was a child. And will they become solid someday?
Oh, they're considered a planet because they are spherical, because they have a strong gravitational field, which clears out the surrounding area. Back when the solar system was first forming, it was formed in a disk of gas and dust that was swirling around the proto star that became our sun. And over time, the planets kind of scooped up all of that material that was in the disk and brought it all together and condensed into a planet. And if the planet successfully cleared its region of the solar system, then that is one of the criteria for being called a planet. The fact that it's spherical in shape, that's another one of the criteria. That means it has enough mass and enough gravity to pull it into that spherical shape. So that's basically why we call it a planet. One thing you got to remember is the word planet actually is a very ancient word. I believe it's a Greek word and it means wanderer. And that word was applied by ancient astronomers to basically any object that they could see in the night sky that wandered among the stars. So planets move from year to year. They change position relative to the background stars. So originally, anything that did that was considered a planet. Even the moon was sometimes referred to as a planet. But nowadays, it refers to these large spherical bodies that are orbiting around the sun or around other stars.
Yeah, and there's no requirement that they be solid.
Yeah, they do not need to be solid, although we do think Jupiter has a relatively solid core, but it's a very small core relative to the size of the planet. Also, if you go deep down into the atmosphere, it becomes so dense, it's more like a liquid than it is a gas. In fact, there's a region where we have what's called liquid metallic hydrogen. It's hydrogen that's so dense, appears to be in a liquid state. And because the electrons around the hydrogen atom are free to move around, it will conduct electricity. So we consider it to be a metallic form of hydrogen.
Also, she wants to know if we can see the planets in the daytime with our telescopes. And yes, we can see Venus and Jupiter and sometimes Saturn very easily. Right. Those are the really bright ones.
Right. In fact, you can see Venus with your naked eye.
Yep.
If you know right where to look at the right time, you can actually see it with your naked eye. But it takes somebody.
It's hard to find. It takes time. I think that during the day, I've only seen it once with my naked eye, and it was completely by accident. I was up in the Sierras backpacking. I was with my brother, and we're up at like 9,000 feet, and we're exhausted, and it's around noontime, and I was just laying back on the grass in this meadow, and I'm looking, and I see this white dot. And I say, what the heck is that? And I thought maybe it was just my eyes. And I got my brother to look in the same part of the sky, and he saw it, and we realized it was Venus. So it's not that easy because the bright blue background makes it tough to pick out anything.
It is very visible, though. We used to very often when I was operating Leia in the daytime for school kids, we would point the telescope at Venus, and then I would use the telescope as a pointer and just kind of line it up, and we could point out to people that you could see it naked eye.
Yeah. And John just mentioned Leia. Leia is one of the 3 observatory telescopes up here at Chabot. We give names to all 3 of our telescopes. Leia is the oldest of our 3 telescopes. And then the next oldest is Rachel, and then the one behind Richard and I, that's Nellie. So we give names to all of them. That's actually kind of unusual for observatories to give names to their telescopes. So when you hear us talking about Leia or Rachel or Nellie, we're talking about our telescopes.
One of the tricks that we try to use on smaller observatories is when you close up the observatory at night, try to leave it in focus. So if you happen to open it during the day and want to look at a planet, And all you have to do is point to the right place, and you don't have to wonder whether you're in the right place or not, because it will already be focused for that planet.
Yeah, that point to the right place part, that's the hard part.
That's the hard part.
Right.
Well, yeah, you just need a computerized telescope.
Yeah, there you go. Yeah. So enough about Jupiter. The next object we would have looked at is Saturn. So I've got an image of Saturn actually taken once again with this telescope. Can everybody see that?
Yeah.
All right.
Yeah.
So this is
Nice.
not. It's a good image. It's not the best I've ever seen. This is one I did. I'm sure Conrad Jung has probably taken even better images than this. But a couple of things I want to point out. You see the rings around Saturn. You can just barely see a dark band on Saturn. Saturn is smaller than Jupiter, but it's still pretty big. It's 9.5 times the diameter of the Earth instead of 11 times. And that's refers just to the planet itself. And then the distance across the rings, well, that's about the distance between the Earth and the moon, the Earth and our moon. So a little over 240,000 miles. And if you look carefully, you can see a little dark band in the rings. That's actually a gap in the rings. We call it the Cassini division or the Cassini gap. And if you get close up to it, it's actually not truly a gap. There are ring particles in it. They are darker and much more diffuse than in the rest of the rings. And then one other thing I want to point out to you, and that's right here. You notice that the rings kind of stop before they get to the limb of the planet itself. And that's because the planet is casting a shadow on the rings. The sun angle is not straight behind us, it's slightly off to one side. And because of that, we can see the shadow of the planet on the rings. And that's pretty cool. Saturn has one big moon called Titan. Titan is one of the few moons in the solar system that has an atmosphere. In fact, Titan has a very thick atmosphere with a lot of methane and ethane in it, along with nitrogen. And Titan is the only other planet that we know of where it rains. Or can't call it a planet, it's a moon, but it's the only other body we know of in the solar system where it rains. And on Titan, it rains methane. Here on Earth, methane is a gas, but on Titan, it's so cold that the methane becomes a liquid, and it rains, and it actually forms rivers and streams and lakes. So when we look at Titan, we can actually see those rivers, streams, and lakes on the surface of Titan.
Are you going to get some of that lakefront property?
Yeah, right. Yeah.
I don't know about the smell there, though. That
Yeah,
methane
yeah.
rain.
Yeah,
Right.
I've got a couple of other images here that I wanted to
I
share.
got a question for you, though.
Okay, go ahead.
The Cassini division, which moon is responsible for clearing out that gap?
Now, have we finished the quiz yet? Can I give that
No.
question?
That's not a quiz question. That's a real question. I'm
Yeah.
curious. Do you happen to know what that is?
Yeah, it's Mimas.
Okay.
Yeah, and you do know that that's one of the questions on the EAS quiz, right?
Oh, I missed the quiz this week. I know there was one. I
don't think the quiz is done.
I couldn't bear to take it because I always miss so many. Yeah.
So I just gave away the answers.
Yeah, well, it's all right. I won't tell Ray if you don't.
Okay. So what I wanted to do is to give you kind of a close-up here of the rings. This is a view of the rings looking down. This was taken by the Cassini spacecraft. The Cassini spacecraft orbited around Saturn from 2004 until 2015. And sometimes it orbited over the poles, sometimes it orbited around the equator. It orbited at different angles, and we got lots of different views of the rings and of its many moons. It has more than 80 moons. Most of them are way too small to be seen from the Earth. And in fact, you see a couple of them here in this image. But you get an idea that the rings that look like, well, there's only 2 or 3 rings when we look at it from the Earth. When we see close up, we see that those rings are actually made up of many, many rings. And this region here, this dark region, that's the Cassini division. So you get an idea what it looks like close up. It's actually, it does have ring particles in it. It's just that they're a lot darker particles and they're more diffuse. So that from Earth, it makes it look like there's a gap in the rings. But there are gaps. You see another gap here. You see this very narrow ring that's called the E ring. It's actually ice particles ejected by the moon Enceladus. And if you were to go close up to the rings, you would see that they're made out of chunks of ice, mostly water ice, in fact. There's also dust and some dirt in there and a little bit of rock, but it's mostly chunks of ice. And most of those chunks are relatively small. A big one might be the size of a small desk. So this is what Saturn's rings look like close up. Like I say, there are a lot of moons around Saturn. And I'm going to switch to a different image here. This one right here. And hopefully I can share that. You see it?
Yep.
All right. So this is looking down on the rings, and you see a moon inside this gap here. And this moon is actually shepherding particles in the rings, causing them to kind of move away from either side of the moon, creating that little gap that you see there, and also shedding material behind it as well. So there's actually several places where we see moons, a number of these little tiny gaps that you see here. There are actually moons embedded in them, and the moons disrupt the rings, either causing material to be kicked out of the rings or causing them to be separated. So that's another interesting view of the rings of Saturn.
It's a remarkable image.
Yeah. Let's see. Am I doing this correctly? I think I'm.
I don't know.
Oh,
What are you trying to do?
there we go. I'm on the wrong image here.
Yeah.
So, all right. So I think that's all I've got for Saturn. The next object we would have been looking at is Mars. And Richard, I think you've got some Mars images,
I'll take that
right?
away. Hold on here. Let me
Right.
get these shared. These are not pictures of Mars from Nellie. What I will do here is let me get shared my screen. Here we go. All right. There is a astrophotographer named Damien Peach who we have mentioned several times during these programs, and Damien is an expert at photographing planets using his telescope here on Earth. Often he goes to the Bahamas or different places in the Caribbean where he gets very good atmospheric conditions and what's called laminar airflow, and he takes video. So what this is here is a video taken of Mars on the 30th of September, and he'll go through several thousand individual frames. Let's say he's shooting video at 30 or 60 frames per second. He will go through each of the frames and he'll take out the ones that are blurry, and he'll leave the ones that are sharp, and then he'll photographically stack the ones that are sharp and create an image that is almost as good as one you might get with a space telescope. And that's how he's able to get this level of detail and this degree of sharpness. This particular image is really nice because it shows off two notable features. The first one, of course, being the polar ice cap. And this is carbon dioxide ice at the polar cap. And the other is this feature here. It almost looks like the shape of Africa on Mars, and it's called Syrtis Major, and it's part of the lava highlands of Mars, which is surrounded by these the lighter colored basins. And what I'll do is actually advance now to the next one. Let me see if I could do this here. Hold on. And this is the one he took on October 7th. Did the slide change, Gerald? Are you seeing the one that says October?
Yeah.
Okay, great. And you can see that it's just a different time of day. Syrtis Major is rotated out to this part of the field, and then you see other parts here. And I think, correct me if I'm wrong, I think this is Olympus Mons.
I think you're right. You might also notice what looks like clouds to both the left and right. Mars does have clouds, so it's not unusual to see them. They're very thin clouds, so they're hard to see when you're looking straight at Mars, but off to the limbs, we because you're looking through more atmosphere, you can actually see that there are clouds there, and they're often carbon dioxide clouds. So Mars's atmosphere is mostly carbon dioxide. It does have water in it,
Yeah.
so we get a little bit of water vapor as well.
And possibly a lot of water under these polar regions,
right.
as is recently speculated because of ground penetrating radar that's been flown on some of the spacecraft that have visited recently. I mentioned Olympus Mons. Olympus Mons is a giant volcanic feature. It's really the tallest volcano in the solar system, right?
That's right.
And it's so tall yet so gradual that you probably wouldn't even really notice if you were able to take a long walk on Mars without freezing to death. You probably wouldn't even notice that you're climbing the largest volcano in the solar system because it's a very gradual rise. You could see that it starts here, the center is here, and then the other edge is all the way over here. This is like the size of continents here on Earth.
Well,
right?
the base of Olympus Mons is the size of the state of Arizona.
Huh.
And the peak is 3 times the height of Mount Everest. So it's big.
It's big, but also very broad.
Right.
So go ahead. Sorry. What were you going to say?
Well, you were talking about Damien Peach, and one of the things he tries to do every time Mars comes around, gets close to the Earth, he tries to take a lot of these images, and he tries to get enough images to where he sees
video,
it
an animation
for the full rotation, and then he will make an animation showing one complete rotation of Mars in high resolution. It's really amazing to see.
I haven't seen him do one this year yet. So he's probably still gathering the information to do that. I have a feeling we'll see one soon.
Well, we just had opposition. Opposition was on the 13th. Opposition is when Mars is directly opposite the Earth from the sun. So imagine a straight line going from the center of the sun through the center of the Earth to the center of Mars. That's called opposition. And that was on the 13th. And the point when Mars was closest to the Earth was on the 6th of October. So
so he's probably still taking a lot of images right
probably
now.
right in the middle of doing it right now. Yeah.
So this last image is by our own Jim Ferreira, who is a East Bay Astronomical Society member, and he is an exceptional astrophotographer. He tends to shoot mostly in black and white these days, and his images here of Mars are no exception to that. Jim, I believe, as well as some of these other, actually this one is I believe is a near infrared image. So he's actually doing some special photography with this to bring out features in higher contrast than you normally would through a red, green, blue image system. So again, you see the basins and the polar ice caps. But one of the things I wanted to mention, if anybody wishes to try to take photographs of the features on Mars, and you have a telescope that's capable of doing it, maybe hook up a DSLR camera to the back of the telescope, maybe put a lens or an eyepiece in between the telescope and the camera to magnify it even further. A lot of people also add a red filter. I know that sounds a little counterintuitive, but if you you put a red filter in front of the camera when you're photographing Mars, you could actually bring out a lot of detail that you otherwise wouldn't see.
Right.
And that's one of the tricks for Mars photography.
Yeah.
I actually would do that on an eyepiece sometimes. Just put a red filter on the eyepiece to try
Right.
to
Yeah. A lot of people
bring
do
out
that.
details.
Yep.
All right. Well, that's what I got on Mars here. Let me stop
Okay.
my share. Yeah.
Well, let's see. Probably the next thing we would have done is start looking at some deep sky objects. One of the ones that's high in the sky right now is called the Ring Nebula, which is a planetary nebula. So I've got an image of the Ring Nebula that I'll share with you. And we've got a couple of other images of planetary nebulas that we want to share with you and talk a little bit about what these are. So hopefully, let's see if I can get this to share here. Yeah, there we go. So this is the Ring Nebula. This was taken with Nellie, the telescope behind us here at Chabot. The Ring Nebula is the remnant of a dying star. It's located in the constellation Lyra. Its other designation is M57, Messier 57. There's a catalog called the Messier catalog, and this is number 57 in the catalog. It's about 2,300, 2,400 light years away. And this is very typical of how stars like our sun end their lives. In fact, most stars end their lives in a similar way. What happens is when the star gets very old, it swells up. It becomes more than 100 times its original size. So imagine our sun in, say, 6 billion years will be more than 100 times its current size. Not good for the Earth. And when it's that big, it's called a red giant. And a red giant star, because it's so big, its gravitational hold on its outer layers of gas is not very strong. And there are strong internal winds caused by all the convection going on within the star. And those winds cause the outer layers of gas to literally blow off out into space. And on a red giant star, when it's at a certain phase in its life, it begins to blow the gas off out into space. This goes on for 100,000 years or so. And at the same time, the star is running out of fuel at its core. Stars produce energy by fusing atoms into bigger atoms. Right now our sun is fusing hydrogen to form helium. Later on, it will start fusing helium to form other things, and eventually you get carbon and oxygen and neon and so forth being formed by this fusion process. But at some point, a combination of lower temperature at the core and running out of fuel at the core, the fusion process stops. And that fusion process is what produces the outward pressure that keeps the star bloated. Now, the star has been losing mass over 100,000 years or so. So it's lost its outer layers and exposed the hotter interior. But the fusion process stops, the star collapses, forms what's called a white dwarf. White dwarf basically is a very small, compact object, but it still has all the heat left over from when the star was, that red giant. That heat is then emitted as ultraviolet radiation. And the white dwarf is surrounded by gas that was blown off by the star when it was a red giant. The ultraviolet radiation goes out and it hits the gas, ionizes it, and causes it to glow. And so what you see is a glowing bubble of gas around the white dwarf. And if you look carefully, you can see the white dwarf right at the center. It's very small. It's only about the diameter of the Earth now. So you imagine a star that was once in the prime of its life, 1 million miles in diameter. It'll shrink down to maybe only 10,000 miles in diameter when it's a white dwarf. And it's so compact that the matter in the white dwarf is called degenerate matter. Degenerate matter behaves in a strange way because the electrons can't jump to higher energy levels. And, that's atomic theory, and a lot of you probably have no idea what I'm talking about. So just know that it's called degenerate matter. So this gas is glowing because of the ultraviolet radiation. Most of that gas is hydrogen gas, and hydrogen gas glows in a very deep red color. And you can see right around the fringes here, the deep red color, but there's actually a lot more hydrogen than that would suggest. In fact, because it's so deep and so deep a red color and not very bright, most of the hydrogen gas that's glowing is actually not visible in this image. If we took a very long exposure using just the right filters, we would see that there's a lot more glowing hydrogen gas all around this thing. In fact, it probably extends right out beyond the edges of the frame here. The turquoise color that you see in here, that's caused by oxygen. Specific type of ionized oxygen glows in that bright kind of turquoise color. And it glows much brighter for a given amount of ultraviolet radiation. It glows much brighter than the hydrogen does. So it overwhelms the hydrogen, and it makes it seem like it's mostly oxygen in this region, but it's actually mostly hydrogen. It's just that the oxygen glows a lot brighter. So this is a planetary nebula. It's called a planetary nebula because when these were first discovered over 100 years ago by astronomers, they thought it was actually a ball of gas condensing to form new planets. But it turns out it's a ball of gas left over from a dying star. So the name planetary nebula stuck, even though that has nothing to do with planets at all.
That was when there really wasn't a good sense of distance, right? So everything, we did not yet have a way to know that galaxies were, millions of light years away, and they thought they were close nebula that were turning into something, other than a galaxy. And the same for planetary nebula. They thought they were close objects like, Jupiter and Saturn.
By the way, you'll hear astronomers use the term nebula quite a bit. And the word nebula just means cloud. There are different kinds of clouds out in space, and they're just called nebulas. This particular type of cloud is called a planetary nebula. Now, the Ring Nebula is one of many planetary nebula out there. And it's often very interesting to see the different shapes that they form. This one looks like a ring. We actually know that this is a more like an hourglass shape. I've got another one, if you'll bear with me here just a second. There is another nebula that looks very similar to the Ring Nebula. It's called the Helix Nebula. And I've got two images of the Helix Nebula that I wanted to show you. Let's see if I can share that again. Too many buttons to push while I'm doing all this. So there you go. Can you see that?
Oh yeah, these are great.
So this is what it looks like if you looked at it through a telescope, took a long exposure. This is actually a Hubble Space Telescope image of the Ring Nebula. And you can, or not the Ring Nebula, Helix Nebula. And you can see it looks similar to the ring. But here is an artist's rendition of what it looks like if you could view it from the side. You see it's actually a bubble with a torus around it. And that is actually very common for planetary nebulas, to actually have a torus around the white dwarf with this bubble of gas, which can have all kinds of different shapes. In fact, just to give you an idea, let me back out of this one. Give me just a second here. We're going to show you one other image in a minute here, but I wanted to share, just to give you an idea, all the different possible shapes there are, or not all of them, but a lot of the different possible shapes. So here are a bunch of Hubble Space Telescope images of planetary nebulae. And you can see they have lots of different shapes.
You know what? I think they're having a Zoom meeting.
You're right. Yeah. Fortunately, they're all on mute, so they're not going
Yeah,
to
they're all-
Yeah, we don't want to hear their comments.
So you notice there's lots of different shapes here. You can see that some of these have hourglass shapes. Some of them have just totally weird shapes. This one I think is not actually a planetary nebula. This one I think is a supernova nebula. I'm pretty sure that's
It looks like the
M1.
crab.
Yeah, that's M1. So that's a
Yeah.
supernova nebula. But most of these others are uh, planetary nebulas. And this one is called the clown face. We used to call it the Eskimo Nebula, but I understand we're
Can't call it that anymore.
can't call it that anymore. So here's the ring. Here's the helix. I don't see the butterfly in here, but there's one that looks like a butterfly. So you get the idea here. There's lots of different shapes. Now, Richard, I think you've got an image.
Yeah, I
that
had
you
one
wanted to
that came
share.
that was released this week, and let me go ahead and give me a sec here to share this.
Sure.
Make sure I'm on the right thing. All right, bear with me here. Screen. Okay, I'll try it this way. I'll go to my desktop. Okay, there we go. Can you see that?
I see.
We're not seeing an
menu.
image. Yeah.
Okay, hold on. We'll try this again. There we go.
There.
There we go.
Okay, got it. All right, so this is a really interesting astrophotograph, and it's probably technically one of the most difficult ones I've seen anybody attempt. The photographer, his name is Yannick Akar, and he published this on a website called the Astrophotograph of the Day. It's a NASA website, and they encourage amateur astronomers from all over the world to submit their best photographs. And it's always kind of special if you get your photograph published on this site. There's actually two objects here. The red background that you see that covers most of the image is an object called Sharpless 2-129. Sharpless objects, there's many of them, tend to be these hydrogen alpha, deep red hydrogen alpha objects covering large areas in the sky. They're kind of hard to photograph because they're so dim, takes many hours, and people kind of develop a specialty in photographing these things. But what's unusual about this particular region is that in the foreground is a planetary nebula called 2014 OU4. All right, so it also has a name called the Squid Nebula or the Flying Squid Nebula. And what's interesting about this one, aside from it being kind of an unusual translucent blue in front of this red background, is that the shape is formed not only by the white dwarf star in the center, but this white dwarf is part of a triple star system. So there's 3 stars here that are inside the area covered by this planetary nebula, and that's what's causing this weird twisted shape. And as Gerald had pointed out last week, some of the shapes that planetary nebula take on are caused not only by the star that's at the center, but by the planets that are orbiting that star. And in this case, it's not just the star at the center, but the other 2 stars that are orbiting that star.
Right.
So I thought it was a very interesting object. And I want to say that this is 55 hours of exposure time using what are called narrowband filters. And the size of the telescope is an 8-inch telescope. It's a typical amateur astronomer, 8 to 10-inch telescope. But what's exceptional about this photographer is that he had the patience and the technical ability to take 55 hours of exposure and process it so well. it's such great detail and great contrast. So anyway, I thought this was quite special.
And no doubt he used a hydrogen alpha filter was one of
yeah, he used narrowband filter. He used hydrogen alpha and oxygen 3. Probably didn't bother with the sulfur, but may have.
But by using that hydrogen alpha, he captured that deep red color that I was talking about earlier. And you see how far it extends from the white dwarf. So if you were to, look with your eye at this object through the telescope, you might see the central region around the white dwarf, but you would not see all that red coloring that you see. That you need to do a long exposure with the right kinds of filters on the telescope.
Now, it's not clear that these two objects are actually associated with one another.
I'll bet they are.
They could be, but I don't know that for sure. The other thing, this is what I was going to ask you about, because it took me a while today to figure this out. I was curious about this name, 2014 OU4. I was saying, what is the OU catalog? I've never heard of the OU catalog. Well, it turns out
it's an asteroid designation.
Well, that's right. Asteroids use this designation. It's a provisional designation, and I found a chart on how this works. So if you have a 2014 OU4, the 2014 tells you what year it was discovered. The O tells you that it was in the latter half of July, and the 4 is this suffix here, which means that it went through all the letters of the alphabet 4 times, and it was now that meant it was the 120th object discovered in the latter part of July in 2014.
Right. Yeah.
And you only use 25 letters in the alphabet because the letter I might be confused with the number 1.
Right. Yeah, this is the method that we use for doing asteroids. All the provisional designations for asteroids use the same format, and we often get asked, well, what does all that mean? And everybody figures out that 2014 means the year 2014, but after that,
what does it mean? So I thought this was a great chart. I had never really learned about it, and I was I'm saying, what is the OEU catalog? The University of Oklahoma? I mean, I had absolutely no idea. And finally, I found an article that explained this, and I was I figured you knew about it.
Yeah, do me a favor, email me, because I get asked this all the time.
I will. This is a good chart. Yep.
Yeah, send that to me. So
okay. Well, I'm going to stop sharing.
So we've been talking about planetary nebulas, and most of the ones we're showing you are a couple of thousand to a few thousand light years away. But I want to go a little bit farther out. Some other objects that we would have looked at tonight, and I want to start with a object called a globular star cluster. And there's 2 of them I want to show you here. So the first one is this one here. This is M2. And M2 is a globular star cluster, and it's kind of a classic globular star cluster. Hundreds of thousands of stars. The stars orbit around the center of the cluster, and the cluster orbits around our galaxy in a region called the halo of the galaxy. So, if you were outside of the galaxy looking at it, it looks like a flat disk with spiral arms in the disk and a central bulge. And then around all of that is this kind of a faint, diffuse region called the halo. And that is where the globular star clusters hang out. There are about 150 or so orbiting around the Milky Way galaxy, and we see them orbiting around other galaxies as well. And like you say, hundreds of thousands of stars in the clusters. These are very old stars, among the first stars to have formed when our galaxy was first forming. It was formed out of about a huge cloud of gas and dust, which had lots of sort of very sort of mini galaxies within it, and it all kind of clustered together. And most of those formed the big galaxy that we know today as the Milky Way galaxy. But some of those little knots of gas kind of stayed out at the fringes and became these globular star clusters. The stars in the cluster orbit in highly elliptical orbits. So they're not circular orbits, they're long ellipses. So they go in and close to the center of the cluster. And during that time, they're moving very fast. And then they swing out to the very fringe of the cluster where they're moving very slowly. And then they swing around and come back in. And they just do this over and over and over again. This image was taken by Conrad Jung, our staff astronomer, using the telescope here, Nellie, our 36-inch reflecting telescope. Now I've got another one, and so I'm going to switch to it here.
Hey, Rick Taft just sent a picture of the ring nebula he took with Nellie last year. You want me to show it real quick? I know you've moved on to globular clusters, but
yeah. Go ahead if you want to.
yeah, hold on for a moment. Let me do that because it's actually it's an interesting image for another reason too. So let me do this. Okay. Thank you, Rick. So this was taken through Nellie last year, and again, this looks familiar, right? Ring nebula, central star. But I want to point out something else over here. Where my cursor is. There's a barred spiral galaxy just hanging out and watching the goings on. But anyhow, that's a neat addition. Most photographs of the ring nebula do not show that. And it stands out very nicely. Great shot.
Yeah. Cool. All right. Well, I've got another image to share here of another globular star cluster. This is much more dense. This is M13, the great globular cluster in the constellation Hercules. It has even more stars than M2 has. It's about 23,000 light years away and well over 500,000 stars in it. And again, they're all orbiting around. You notice how dense it is near the center of the cluster. And that's because that's where all of the stars sort of come together. They're in these elliptical orbits. And, when they're out and the fringes, they're all kind of separated. But when they're in close to the center, they're all kind of close together. If you lived on a planet orbiting around one of those stars near the center, you wouldn't have a nighttime because there would be so many stars so close to you, they would just light up your night sky. It would be like having, 100 full moons in your night sky. In fact, can't remember, was it Asimov or Arthur C. Clarke who wrote the short story called Nightfall about a civilization living on a planet that had a nighttime once every 100 years because all the stars aligned themselves just right so that they could get a nighttime once every 100 years. So globular star clusters. So, one of the questions we often get asked is, what's the farthest thing we can see with this telescope? And certainly we can see galaxies, which are millions of light years away. And we've shown you globular star clusters that are tens of thousands of light years away, and planetary nebula a few thousand light years away. But depending on how bright the object is, we can actually see much farther than that. And John Curry has an image, it was actually taken by Conrad Jung here, but he's going to share an image that Conrad took of the most distant object that we have ever been able to see with this telescope here at Chabot, our 36-inch reflecting telescope. So, John, if you want to share that image.
Yeah, I'll do that. So, let's see. Is this coming up all right?
And it's a picture of his couch.
Yeah. How do I do this?
So click on
there we
share.
Go. How's that? Can you see that?
No.
We just see you, which is okay. But
you click on the share button, and then you have to pick the image from your.
I have to get down there and do that again. Hang on a second. That's not coming up. Why is this?
What you could do is share your desktop and then just open it that way. That's another option.
I'm not getting.
Yeah, there we go. Now we're getting something.
Yeah, but that's not what we want here. How about? Yep.
That
I just
doesn't look
lost.
good.
I just lost Zoom altogether here. What?
Well, you're still in there. So, but actually hit don't send. Click the button that says don't send.
Yeah.
And it didn't clear because we've got the picture of the quasar there, but it's covered by the dialog box.
Oh, well, that's no good.
Yeah.
What if I go full screen with this? Does that help?
Yeah, maybe.
No.
Try disabling your share again.
All right, let's try that again.
And yeah, you know what I'm going to do? I'm going to have to.
Unshare my.
I'm going to unshare your screen.
Because
Okay,
I
so
can't get to the.
Your screen is now. Go back to here.
If you can't get it, John, I've got the image, but
yeah, why don't you put it up?
Yeah, how did
There.
do you go full screen with the image and then share?
Yeah, that's the way I usually do it.
Doesn't-
Yeah, Gerald, why don't you bring it up?
okay. All right.
I get a list of things to share and it doesn't show what I want to share.
Okay.
There we go.
I'll have to work on that.
My
that's the
image
image.
is not quite as big as John's. I'm not sure. Can I?
Yeah.
You try it. Yeah, there you go.
There we go.
But you can see the little fuzzy dots there,
right
the A
there.
and B. Yeah, those are actually an image of the same object. I'll explain why there's two of them in a minute here. But what that is a quasar. And a quasar is basically a galaxy with a really bright beam coming out of it. The bright beam comes from matter falling into a supermassive black hole at the center of the galaxy. And if circumstances are right, it causes it to eject a very, very high power beam of energy, all parts of the spectrum just about.
And also a lot of X-rays as well.
Yeah.
The whole spectrum.
Yeah.
Of energy. Yeah. So what happens is if that happens to be pointing in our direction, and in this case it is, that beam shows up as a visible light, and this happens to be about 8.7 billion light years away, almost 3/4 of what we consider the known universe. So that's that's the most distant object that we have recorded with Nellie.
And why?
The reason you see two of them is because there's something in between us and that object. There's actually another galaxy. That galaxy can't be seen because it's not bright enough, but it is causing what's called a gravitational lensing effect, and it's splitting the image into two. So we see two of them, but they're actually the same thing.
And the reason that happens is one of part of Einstein's theory of relativity says a very massive object will bend light, and so that big galaxy that's between us and the quasar has a lot of mass and a lot of gravity, and the gravity just bends the light coming from the quasar and causes that double image.
Yeah, so part of the light went above the galaxy, part of it went below it. There's actually, from what I've read, there's actually a cluster of galaxies in between us there that are affecting the light. But primarily it's one galaxy that has split it up like that.
Okay, but it's the important thing to note is that even though it looks like a double object, it's a single object.
Right.
It's a single bright quasar that is being optically split by the gravity of a foreground galaxy.
Right. That galaxy is about half the distance a little less than half the distance between here and the quasar.
Got it.
And
so what's the distance again to the quasar?
Roughly 8.7 billion light years.
Just round that off to 9 billion.
Okay.
Yeah. It's an easy 9.
Yeah,
Right.
Yeah, I'll bet Elon Musk's Tesla will be there in no time. Which, by the way, it is now approaching Mars.
Yeah.
Ah,
So it is
maybe
now.
we
We
can
we can now. We used to joke about taking a drive to our nearest planets,
get
but now it's like we have to come up with a new joke.
maybe we can get Damian Peach to image it.
Yeah, right,
Yeah,
right,
there
right,
you go.
All right. Okay, well, how about let's take some questions from Facebook and answer those, and then we can wrap things up here.
Well, we got the quasar questions. Thank you, Becky. Those were good questions. Let's see. Anybody else? Okay, this is a good question from Laura. How in the world do you know, for example, that it's a quasar when so many dots look exactly the same to the novice's eye? So how do we know that's a quasar? How come convince me they're not just two stars?
Well,
It has to do with the red shift
Okay.
that they see in the imaging.
yeah, the other thing keep in mind is that image was taken with this telescope behind us. There are much better images taken by other telescopes, much bigger telescopes like Mauna Kea in Hawaii and the Hubble Space Telescope and so on. So,
Okay, but the important thing was what John said. He didn't explain what that was. So the red shift is if you look at that quasar with a spectrograph and you look at the absorption lines from the light that is reaching the instrument, you'll see that it's shifted to the red side of the spectrum by a certain amount. And the amount of that shift is proportional to the distance of the object from us. So the greater the red shift, the farther it is away. And all of these years that we've known this, we've created essentially, a calibration model. So we could look at an object, we could look at the red shift, and we could estimate how far away it is. So because it's that bright and that far away, we know it's not an ordinary star because it's incredibly bright. It's the brightest known thing that we've ever observed is a quasar. So that gives us a clue that it's not just an ordinary dot. And the fact that it's so bright and so far away, and it fits the theory of what happens when you have a supermassive black hole with material falling into it aimed at the Earth. Right. So that's where we're at in terms of trying to understand the difference between a quasar and an ordinary star that might be in the foreground.
Yeah. A couple other questions that we've seen on Facebook. First, an observation. Margot's daughter. Margot, you didn't tell us what your daughter's name is, but Margot's daughter says that image that you had a while ago of the planetary nebula surrounded by the cloud, the kind of blue planetary nebula surrounded by the cloud. She says that looks like a blue crystal with a hand holding it. So that's pretty good analogy. There was a question also about whether or not we were able to observe exoplanets with this telescope. And basically, the answer is no. Exoplanets are, even though they're orbiting around the star and there is some distance between the star and the planet, because the star itself is so far away, we would just see the glow of the star. However, if the exoplanet happens to pass in front of the star, we can see that the star dims slightly, and we can actually measure that with this telescope. And we can't see the planet itself, but we can see the dimming of the star that's caused by the planet. And we actually used to do that quite a bit here at Chabot. We don't do it anymore, but we used to do that quite a bit.
This is a good question. Is the type of lensing that you were talking about, John, connected to dark matter or dark energy? And this is like, where's Alex when we need when we need him?
Right.
Right? Yeah.
Yeah, I can't answer that question.
The galaxies, and there may be more than one galaxy between us and the quasar. Um, they are composed of what we call baryonic matter, which is the stuff that you and I are made of, the light matter, if you will. But the galaxies also have dark matter in them. And so the combined mass of the baryonic matter and the dark matter produces the gravitational field of those galaxies. So, yes, the dark matter is contributing to the total gravitational pull of those galaxies, which contributes to the bending of the light.
And if I'm not mistaken, the study of galaxies and galaxy clusters that exhibit gravitational lensing, and that they actually do the lensing, has contributed to our estimates and understanding of dark matter in the first place. So we see something that has a certain amount of visible mass, but it's lensing as if it was denser than
Right.
what we actually see, and that contributes to support of the dark matter theory. Now, dark energy is a whole different thing. So the answer regarding dark energy is no, because dark energy is something else entirely other than having the word dark in it. But the dark matter, the answer is yes. It does contribute to the overall gravity that is bending the light.
We have another question. Why are galaxies planar rather than ellipsoidal? Well, that's not the case. They're all different shapes.
Yeah, there are ellipsoidal galaxies as well. But however, ellipsoidal galaxies tend to be galaxies that have undergone a number of merges with other galaxies, whereas sort of prime of their life galaxies tend to be flat spirals. And they're flat spirals because they formed out of a huge cloud of gas and dust. As that cloud began to shrink and condense, it started to rotate. That rotation caused it to flatten, and eventually all the stars, or most of the stars, formed within a flattened disk, which is the typical spiral galaxy that we see. But there are elliptical galaxies, and like I say, they're often be the result of mergers between several galaxies. All right. Other questions?
Well, Joe already answered that one. Somebody had asked, what is an exoplanet? And Joe answered correctly. An exoplanet is a planet around a star outside the solar system.
Okay.
I think that's it on questions.
All right.
There was one question. How is it possible to find these nebula when the universe is so vast? Well, we've got a lot of people with telescopes, and been a very popular thing to do, to look all around the sky. And most of these things that we've shown you pictures of have been around for a long time. We've known about them for a long, long time.
Yep.
And another thing to note about that is, decades and decades ago, some of these objects, would have shown up as a smudge on a glass plate, right? Or on a sky survey, it would have looked, oh, there's something there. But the technology has gotten so good, and especially the ability to process the data to bring out detail has gotten so good that we can go back to objects that were discovered decades ago, photograph them essentially for the first time, and see detail and characteristics that were unknown when the object was first discovered. So a lot of it is the process of rediscovery. We have telescopes that regularly do surveys of the entire visible night sky, and people pore over this stuff and they say, oh, I wonder what that is over there. So there's a lot of new stuff, but it's also a lot of old stuff that's just simply been, studied with better data.
Yep. And as we do that, sometimes we realize that something we thought was one object turns out to be something different.
Yep.
100 years ago, they didn't think the universe extended beyond the Milky Way. And they thought those fuzzy spiral things were actually nebulas, clouds within the Milky Way galaxy. And it wasn't until the 1920s that they realized, hey, those things are actually outside of the Milky Way. And all of a sudden, the universe got a lot bigger.
A redshift.
Yeah, that's why so many things were called nebulas.
Yeah.
And nebula just means, cloudy, unknown object.
Yeah. All right.
All right. Thanks, everyone. This was fun.
Yeah,
Even though we couldn't do live views, I think we covered a lot of ground.
Yeah,
tonight,
I think we'll have clear skies next weekend.
Yep,
So we'll
certainly
be
hope
back
so.
to
Keep our fingers crossed for
the
that.
camera on the telescope. So
All right. Well, take care, everyone. You have a nice
see you guys
weekend and
next
good week.
yeah.
Okay. Good night,
All right,
everybody.
good night.